Having as much fun as I am? I sure hope so, because this is a blast, don't you think? Come on! You can have a better attitude than that. That's it. There you go. Okay. I'm excited too. We're right now in section 1.9, Algebraic expressions. Yeah, that's how you pronounce that. Algebraic. And what we see here is a lot of letters mixed with the numbers. And of course these letters are called variables. And this x squared y cubed, or a, or cb to the fifth, those are called variable clusters. Now the truth is, I made that up. Variable clusters, I mean. No one else calls them that except in my book. But it's so much easier to talk about things when we say, oh, well, we know what the variable cluster is. And you'll notice that sometimes a variable cluster might be just a single variable. But here's kind of a cluster of variables with their exponents and things. Okay, and look, there's no variables at all. I wonder about 7. Don't you? Yeah. Let's go ahead and get right to example 1. As always, I'm going to be going over the examples. There's more in the reading that I'm expecting you to do. And it's good if you can read this before the video, see the video, and then read it again afterwards. And hopefully it'll all make perfectly good sense. The coefficient. The coefficient, which is what we're supposed to put right here, is the number that's multiplied times that variable cluster. In this case, it would be the 8. In the second one, it's the 3, or here it's 2/3. Called a coefficient. Say it with me. Coefficient. 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 Well, you can practice that on your own time. Oh, -6. Yeah, coefficient can be negative. Can be a fraction, as we saw in 2/3. And the coefficient's 7. The thing is, we don't see a variable, so when there's no variable, we have another name for the number that's right here, and that's called a constant. I'll just kind of circle that and write constant. Now the variable cluster, again, is that variables with, that are, multiplied together, and they've got the exponents, and yeah, this is all multiplication in here. 8 times x squared times y cubed. The variable cluster is just the x squared y cubed. Here, in the second example, it's just a. Just a. Just the letter a. It's a variable, stands for some number. C, b to the fifth, would be the variable cluster. Here, x to the fourth. So it's the exponent along with the variable. Here, x squared. And here, of course, there is none. There's no variable cluster there. Simple enough? I hope so. Let's move on. Example 2. Here we have our terms, and we're asked to identify, again, the coefficient and the variable cluster. The difference here is that each one of these terms, we don't see a number multiplied in front. We don't see a number. And when we don't see a number, the number that's being multiplied is... Wait. You all said it. Say it together now. 1. Say it again. 1. Yeah, that's right. When we don't see the number, we're multiplying by 1. This is 1 times x squared y cubed. Well, this one's, we put the 1 here, it's -1 times a, right? And here it's -1 times x to the fourth, and that's 1x squared. But the bottom line is this. If we don't see a coefficient, then the coefficient is 1, or -1. And it's not a bad idea to just put it right on in. Sometimes we say, oh, it's the invisible one, and we can make it visible. There it is. But here the coefficient is -1, and here it's 1. The variable cluster, unaffected by all this. The variable cluster is x squared y cubed for the first one. It's, again, just a, the second. Here it's x to the fourth, and here it's x squared. Okay? So that's just getting you used to some of the words that we use in these algebraic expressions, which are made up of all these terms. Notice we're focusing on the terms here. Okay, next slide. Example 3 and example 4. Now, I wonder what we're supposed to do here. Oh, identify the terms. So in number 3, we're supposed to identify the terms, and we'll just put a comma between them. I see in this first one here 3 terms. I see 7x squared, and 6x, and 1. If we needed to, we could say that that's a positive 7x squared and a positive 6x and a positive 1. Here the terms are 5x and 2. I can just write that in, 5x, comma, 2. So there are 2 terms. This one here looks like 4 terms. Negative 3a to the 5th is the first one. 2a cubed is the second term. 4a is the third, and of course 9. And this last one has only 1 term, so I can list it. Simple enough. Yeah? All right. Now, what's different about example 4 here is this idea, and this is an important idea, that even though I see 7x squared minus 6x and minus 1, that the sign in front of a number belongs to that number. So that is actually a negative 6x. We see, when we say it, minus 6x. But as far as a term is concerned, that's a negative 6x. So when I list the terms here, the first one is 7x squared. The next one is a negative 6x. The third term is negative 1. That's right. Again, the sign in front of the term belongs to that term. In the next example, 5x squared is the first term. Negative 2x is the second term because of the sign in front of the term. By the way, look back up here at example 3. Notice how this term is negative. It's the first term. All the others were positive, though, because of the plus signs. So the sign in front of the term belongs to that term. And we're going to see this especially important idea in, I think it's chapter 4, when we get into what are called polynomials, because polynomials are terms as well, and we're able to switch the terms around. We'll even do this in chapter 2 some. We'll switch them around. Well, we need to know whether a term is positive, like it is right here, or negative, like it is right here. And when we move them around, that sign, as we'll see, will need to move with the term, because that term is a negative 2a cubed no matter where it goes. It could fit anywhere around here. Well, let me just complete this one. The terms of this, I guess that's part C, yeah, is 3a to the 5th is the first term, negative 2a cubed is the second term, negative 4a is the third term, and positive 9. I didn't put a plus sign, but that's what it is, positive 9. Okay? Example 5. Again, I'm just going through the examples. I do expect you to be reading the book here. Identifying like terms. I'm not going to do anything with them except just to identify which ones are like terms. And the like terms are oftentimes easy to identify. Here's a 7x and a negative 6x. Those two are like terms. Here, negative 2 and positive 9 are the like terms. They're both constants. Constants. They don't have a variable cluster with them. They're constants, but they're like each other in that way. Now, in letter C, 3a squared is a like term with 4a squared. But 2b cubed is a like term with 9b cubed. And down here, the negative 15y, the 6y, and the negative 3y, all three of those terms are like terms. What makes the difference? What makes something like terms? As you've done in the reading, it's the variable cluster, the x, or without a variable cluster altogether, or the a squared and a squared, and b cubed and b cubed. Separately, those are like terms. Here, y. Forget it. It wasn't worth doing that. In this next one, there are no like terms. 4x and 6y and 7, the constant, negative 7 actually. Nothing, because the variable clusters are all different, or this one doesn't have any at all. In letter F, oh, so by the way, we can say here none. None of the terms are like terms. or just no like terms. Anyway, 5ab, negative 8ab, plus 3b, positive 3b. This one is missing something, and that means it's not like the others. Only the 5ab and the negative 8ab are the like terms. And in this last one, letter G, I see all x's, but because that's x cubed, it is not like this one, which is x squared. Different exponent means not like terms, or they're unlike terms. But yeah, none of these are like terms here. That's got an exponent we don't see. It's an exponent of 1, actually. But they're not like terms. Nope, 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 nope. Combining like terms. What do we do? That's what we do with them. We don't just identify them. We actually will combine like terms together. And I'm going to write down A, B, and C. Sometimes we can write them vertically. Like in letter A, we have 10x plus 4x. And we can add these and say, oh, well, that's 10 of those and 4 more of those. That's 14 x's in all. 10 x's and 4 x's makes 14 x's. And letter B, 12b to the 4th. And 7 plus 7b to the 4th. That's 19b to the 4th. 12 of them and 7 more of the same thing is 19 in all of that same thing, of those b to the 4th. And letter C says 2h plus 3h plus 6h. That adds up to 11h. 2 and 3 is 5. 5 and 6 is 11. So we have 11 h's in all. So we can write it vertically. That's what this means, vertically. Or oftentimes we'll write them across this way, horizontally. And we'll add this way. So let's see. 7x plus 6x is 13x. Negative 2 plus 9. Those are like terms because they're both constants. They have no variable cluster at all. Negative 2 plus 9 is simply 7, positive 7. Negative 3a squared and positive 4a squared. Well, how much a squared do we have? Negative 3 plus 4 is a total of positive 1. So we have 1a squared. But just like the idea that we can place a 1 when we don't see any coefficient at all, the invisible 1, and make it visible, likewise, if a term like this one right here has a coefficient of 1, we don't need to show it. We can write this just as a squared. In fact, I'm going to write here, or a squared. And this is actually more common to write it as a squared like that, and not the 1a squared. The 1 is helpful at times, and sometimes it just gets in the way. Okay. 4y, so here, this can be helpful. Look, 4y plus 1y. Compare that with 4p plus p. These are actually very much the same problem, g and h here. This one does not have a 1 in front of it, but we could put one, couldn't we? Yeah, we could put one right here. And this one, this letter G does have a 1 in front of that y, but we can just add those together directly. 4y and 1y is 5y. Likewise, 4p plus 1p is 5p. Good. Y cubed, y cubed, y cubed. The variable clusters are exactly the same. So we end up adding the coefficients. 15 plus 6 is 21, plus 3 more is 24. 24 y cubed. And here negative 2, let's check the variable cluster, because this is starting to get a little confusing. X squared y cubed, x squared y cubed. Exactly, the same. Exactly the same. So it's just a matter of combining their coefficients. Negative 2 of them and positive 9 of them are 7 of them. So equals 7 x squared y cubed. Let's see this last example, letter K. Make sure x to the fourth, y to the fifth, x to the fourth, y to the fifth. They are the same. Well, you know something? They are the same here, but I noticed in the book that they weren't supposed to be. So I kind of messed up. Let me cross that out and start fresh. Sorry about that. Here's what it was supposed to say. 2 x to the fourth, y to the fifth, plus 9 x to the fifth, y to the fourth. I thought this was supposed to be a little bit off. And these are not like terms. They're close, but they're not like terms because x to the fourth here, x to the fifth on this one. Yeah. X to the fourth on one, x to the fifth on the other. They're not like terms. Y to the fifth on one, y to the fourth on the other. Not like terms. I see the same variable x and y. I see even the same exponents, but they're switched around. So they're not like terms. Have I stressed that enough? So I'll put this two ways. First of all, I'll say not like terms. And then I'll write the real answer is, or an answer I should say, cannot combine. Cannot combine. That's because their variable clusters are different. They're different. Okay? I hope that makes some sense. Oh, let me just go back a slide here and remind you that here we had no like terms, and that's because the variable exponent was different. So there's not like terms when we identify them. They're not like terms. Okay. Now this was example 6. I'm going to skip example 7. You can do that one. It's very similar. You can do it. In fact, so is example 8, which we've gone on to now. Notice we're at example 8 now. The only difference here is that some of the coefficients are negative, and so that's just going to, work itself out. But otherwise, things work out very much the same. This is going to be something W, and it's -7 and -2. That's a -9, so it's -9W. This is going to be something x squared, and it's 3 and a -5. You can think of it as a +3 if you need to, and a -5, which is -2. Here, these are like terms. Something x, -18 and +6 is -12. Oh, here's where it might be. I see 1y. I'm going to write the 1 in. -9y, +1y, something y. Let's see, -9 and +1. It's -8. And here the same. They're p. -2 plus 3 is 1. Oh, here's one where we can just write it as p. We don't need to write in the. We don't need to leave the 1 there. We're allowed to not have to write it in. Here's on letter F also a 1. So that's you don't have to write that invisible 1 in as 1, but I like to. -1c and +7c. How many c's is that? 6c. Okay. Ooh, this next one we better, before we do anything, change this to adding the opposite. I'm going to rewrite this as -m plus 6m, and then decide what it is. I'll put a 1 here for the -1m, plus 6m is 5m, +5m. Here's another one. Letter H has the double negative. We'll change it to positive before we figure out what it is. Let's see, so that's going to be 3x plus 4x, and then it becomes quite simple, 7x. Like terms, x, -4 plus 4. Yeah, that's 0. Now, 0 times x could be thought of as 0x, but it's also just 0. Because this is really 0 times x. And 0 times anything is 0. So we can write it with 0, and we don't need the variable at all. And this very last one cannot combine. Again, because they are not like terms. One is a y squared and the other is a y term. Okay? That's example 8.